Okay. Oops, sorry. Okay. Okay. Saat ni. Okay. Is it clear to you? The slide?
Yes, Doctor, clear.
Yes, okay. Alright, good. Okay, so topic number 4 is about design of ideal reactors for single reaction. Okay, so you will use some of the subtopic from the previous topic, which is stoichiometry and matter balance, and you will be applied to this topic. Okay, so this is the looks like a mind map. Okay, if you can see, number 1 is the Moore balances, red law, stoichiometry, and the fourth one is the combination. Okay, so this combination is including the number 1 and number 2 and number 3. Okay, so that's why you have to have a good knowledge. You need to have a good understanding from the previous topic. Okay, so this is the Moore balance. Okay, for PFR, CSDR, and batch. Okay, so I just recall how do we get this equation. Okay, so let's say we have a system. Okay, this is a system. Okay, and there is a volume for the system. Okay, and there is a flow in. Okay, and there is a flow out. Okay, and there is a reaction occurs. We denote it as a GA, and there is the accumulations of molecules A here. Okay, so basically the general equation of the matter balance would be FA naught minus with the FA plus with the different integration of the RA dV is equals to dNA over dt. Okay, so the matter balance would be applied same for all these 3 types of reactors. It's just that you have to make some changes according to the type of the reactor. Okay, so let's say this is a batch, which means there is no out and in. Okay, so you can cancel it to 0. Okay, there is an accumulation, okay, in the reactor, and there is a reaction occurs. Okay, but you need to remember for batch, the V throughout the time will be same as the V naught. Okay, there's no changes of volume. Okay, so you cannot integrate with the respect of the volume. There's no changes of volume. Okay, so here you need to rewrite it to become RA V, okay, is equal to dNA over dt. Okay, so how we get this equation? You need to differentiate it. You need to have a differential equation in terms of dx over dt. Okay, so you have to expand this equation. Okay, so from here we can put in one side 1 over V dNA over dt is equals to RA. Okay, so this one you can expand it. Okay, so I letak jelas nanti you confused. So RA is equal to 1 over D NA over dt. Okay, so this one you need to convert, you can make it as a CA sebab RA ni selalu kita dalam bentuk CA. Okay, okay, you boleh buat as a D NA over V, okay, over dt. Okay, so this become dCA over dt is equal to RA. Okay, so from here actually, okay, you can expand it dNA over dt. So what is dNA over dt kalau you tak nak dalam in term of CA? Okay, so you have D over dt, which is, what is NA? NA is NA naught minus with the NA naught X. Okay, so you cannot differentiate NA naught with respect to T is equal to 0. Okay, so ni akan jadi, you can cancel to 0. So it become dNA over dt. Okay, so NA naught is a one value, so you can put at outer side, so become NA naught. Okay, dx over dt. Okay, so make sure this you put a sign of negative sebab ada negative here. Okay, so just rearrange it. Okay, so n naught dx over dt. Remember what is dna dt? Dna dt is equal to RAV here. So just put it as n naught dx over dt, replace dna dt ni dengan RAV. Okay, that's why you rearrange it, you akan dapat this one. Okay, clear everyone? Okay, so for CSTR pula, okay, we have a system here. There is a stirrer, and then there is a in and there is a out. Okay, so from here, you have a same apply with this general equation minus with the FA plus with the RA dV is equal to dNA over dt. Okay, so for CSTR is the same as PFR. It is unsteady state. It's a steady state, sorry, so should be 0. Okay, so what remains is FA naught minus FA plus RA dV. Okay, remember what I've told you before at the end of the topic number 3. For CSTR, there is no integration and diffusion equation for CSTR volume. Okay, because this is well mixed, means that there is no changes of volume occur since ada masuk and ada keluar along the process. So the volume here does not change. Okay, so this one we should write down as a RAV. Okay, so tinggal FA naught minus with the FA plus with the RAV is equal to 0. Okay, so make sure you make it as a equation of FA naught dengan X, which is FA naught minus with the FA naught minus with the FA naught X. Okay, this represent the FA. Alright, is equals to negative RAV. Okay, so this one you cancel it and it becomes you arrange it FA naught X over negative RA. Okay, so this is how you get lah for CSTR. Okay, so for the PFR nanti akan tunjuk. Okay, so under the red law we have this is elementary one. Okay, which is according to the stoichiometry, we have the first order, and we also have another one. Okay, this is in a multiple reaction. Okay, you will learn dekat chapter after midterm break, and then we have this is for the reversible. That's why you have a KE here, equilibrium constant. Ni pun you akan learn nanti. Okay, so for the stoichiometry, remember we have in term of the F and in term of N. So F is flow. Okay, N is the number of moles. Okay, so number of moles is referring to the batch. Okay, whereby in batch, whether we have ideal gas for variable volume, and another one is liquid gas in a constant volume. Okay, so constant volume should be V is equal to V naught. This one, V besar, okay, is equal to V naught 1 plus epsilon X and so on. For flow pula, we have a liquid and ideal gas. Okay, for liquid, constant flow rate is in terms of volumetric flow rate will be remain the same, alright, throughout the time. And then for ideal gas, same like the ideal gas variable volume for the batch, it's just that you replace the V capital with the small letter of ni lah, jadi volumetric flow rate. Okay, so at the end, what you need to do is you need to have in terms of concentration. Okay, make sure you convert all the flow and the number of moles into the concentration. Okay, this is you learn in topic 3 lah. Right, so from here you need to get what is V ataupun T. Okay, T or V. Okay, so how you do this? You have to combine from the mole balance. Okay, for example like PFR here. Okay, nanti akan explain more lah about this sebab tak cukup ruang nak tulis. Okay, so dx over dv negative RA Fn. Okay, kalau you see this is negative RA. So this negative RA will change according to the red law. Okay, so red law here katakan this is first order. So it will be negative RA is equal to KCA. Okay, so just replace this one KCA over with the FA naught. Okay, so here you have to expand, alright, what is CA? So CA referring back, okay, CA is equal to this one. Okay. Okay, for this one kita assume dia adalah kenapa ni? Ni. Okay, PFR. Okay, so daripada situ replace the CA. Okay, so you akan dapat this equation. Okay. Alright. So macam mana we get the volumetric flow rate ni? Because if you can remember, CA naught is equal to FA naught over with the P naught. Okay, just replace it with this one. Okay, you will have P naught here. Okay, so from here you need to integrate it. We have in term of X dengan V. Okay, so you have to integrate F dV kat sebelah sini dengan F dx. Okay, so to get the V here equal to something like this. Okay, ni nanti I akan terangkan. Okay, alright, so the lecture outline, we will start with the ideal batch reactor and then followed by steady state mixed flow reactor and then steady state plug flow reactor, PFR and PBR. And you also learn how to calculate the space time and space velocity and holding time and space time for flow reactor as well as size comparison of single reactors. Okay, sebab for the topic number 5 you will learn multiple reactors. Okay, so at the end of this chapter, students should be able to analyze the characteristic of ideal reactors according to the design equation. Okay, that's why you have begin with the material balance. You have to know how to modify or change the material balance according to the characteristic of each of the reactor. Okay, and then discuss and determine the design parameter of reactor, which is space time, space velocity, holding time, and compare the reactors in terms of its size and volume. Okay. Okay, so this is the ideal reactors. Okay, the figures for the batch, and we have a CSTR and PFR. Okay, this is like a pilot plan, pilot scale lah. Okay, small scale. Okay, so usually ideal reactors are useful model which are easy to treat. Okay, sebab in a real system, okay, the batch CSTR and PFR ni we treat as non-ideal reactors. Okay, sebab we're not looking into one factors only. Okay, for example, for the process, okay, in the CSTR, okay, the process is not affected by one parameter only, such as temperature. It also can, depending on the nature of the feed, nature of the reaction, okay, the feed. Alright, and lagi get the pressure inside and so on. Okay, so we cannot measure all these parameters at one time. So what we can do is we can make it as we assume as an ideal reactors. So untuk CRE ni, CHE502, you akan assume all the processes in ideal operations. Okay, for example, kita akan treat it as in ideal reactor. Our basic is, okay, basic function is to find X conversion for a given size of reactor, and kita akan relate the size ni pula dengan concentration, and to find, okay, size of reactor of a reactor for a given concentration. Okay, so that's why nanti you akan belajar macam mana how to to get the design equation in terms of the concentration and also in terms of the X in order for you to get the V, the volume, okay, value. Okay, so this is the industrial reactors example. You can see this is a batch manufacture of colorants. Okay, so this the top reactors is on the floor level. Alright, so underneath there is a whole reactor lah. Okay, so ni adalah dia punya point untuk feed lah, masukkan raw material. Okay, dia ada yang bawah tu adalah submerge bawah dia. And then we have a CSTR manufacture for polyethylene. Okay, polyethylene ni kita buat as a PE lah. Ini adalah crystalline structure of a thermoplastic, This chemical you can find it in a plastic bag. Okay, the one of the components, chemical components to produce a plastic bag and other medical devices lah application. And then we have a 3 units of PBR at N oil refinery. Okay, packed bag reactor. Selalunya untuk catalyst lah, untuk melekatkan catalyst. And for kita ada 3 of reactors in series. Okay, so the first one usually is for the to produce is a reaction between aromatic hydrocarbon and hydrogen. And then the second one is the isomerization process. And the third one is the what do you call it, cracking process. Okay, so this one is to crack it to become a like ethyl benzene product, methyl benzene, okay, which used a lot for polymer industry. Okay. I can hear you are singing a song. Okay, so and then we have an important terminology that you need to know, okay, which is the RE, rate of reactions. Okay, so this is the unit. Okay, it won't change. Is the unit that change is in terms of K saja. K ni adalah depends on the order of reactions. And then we have a conversion, reactor volume, volumetric flow rate, concentration, number of mole, and molar flow rates. Okay, molar flow rates, the unit would be is mole per second. Okay, so this is the equation of mole balance on species J. Okay, species J can be anything lah, A, B, C, D, and so on. Okay, so rate of flow of J into system means that the unit is in terms of mole over time. Okay, and then we have minus out. Okay, plus with the generation here. Okay, then we have accumulation here. Okay, so basically this is the material equation lah, the general one. Okay, so here for GA here, alright, let's say it is in terms of the in batch, so it will have RAV. So RAV, okay, katakan RA, okay, RA tadi adalah concentration of time, okay, which is mole over decimeter cube over with the time. So V is a decimeter cube, so you cancel it. Okay, you will have the same unit like Fn0, Fa, and Tno and Dt lah. Okay, so this is the one. Okay, tak payah terangkan lah dah ni. Okay, so for batch reactor, the characteristic is, okay, has neither flow in nor flow out of reactant or product. Okay, so this one we can cancel it as 0 while the reaction is being carried out. Okay, so we have this one. Okay, and it operates at unsteady state. Okay, there is the accumulation, so there is a dNA over dt remain in the equation. Okay, so the reaction is perfectly mixed, thus no variation in the rate of reaction throughout the reactor volume. Okay, so if you can see the volume here, okay, with respect to the change of time from T0 to T1 to T2, the volume still the same. Okay, so this one has to be replaced with the RAV. Okay. Okay, so this one just rearrange the equations. Alright, so once you rearrange it, you have to do some integration. Okay, like F T naught. Okay, just put it here, and this one akan turun ke sini. Okay, dt, okay, is equals to F NA naught dNA over dt. Okay, so that's why you will have this equation lah. Alright, oh I lupa nak letak, sorry, ini bukan dt, this is RAV, dt dah naik atas. Okay, so that's why you will have this one. Okay, so the next slide I will show you, let's say if this RA, you replace it with negative KCA or negative KCA2. Okay, okay, so these are equation in terms number of moles. Okay, if the rate law is first order, which is negative RA is equal to KCA. Okay, so we want to get this final equation in terms of T. Okay, so RAV is equals to DNAT. Okay, remember yang daripada mole balance, we have RAV is equal to DNA over DT. Okay, so kita expand the equation. So RA is equals to negative KCA and V here. Okay, so here we can change the CA becoming NA. Okay, so what is CA? CA is equals to N over V. Okay, ataupun letak N besar lah, NA over V. Okay, so NA is equals to what they call it, NA is equals to CAV. Okay, so just replace it, so cancel lah V sebab this one CA is NA over V, so kita cancel, so this remain. Okay, so we have a negative RAV is equals to negative KCAV is equal to negative KNA over V times with the V. So it become negative KNA RAV here. Okay, ni RAV, sorry, apa sebanyak salah cakap ni. Okay, so daripada sini kita remember what is RAV. RAV is DNA over DT. So just replace it, DNA over DT is equal to negative KNA. Okay, so integrate in terms of number of moles of A and also T. Okay, you will have FT1 to 0 DT is equal to, just rearrange here, 1 over K FNA NA naught 1 over NA DNA. Okay, so you integrate kalau 1 over NA DNA, it becomes ln, okay, NA minus with the ln NA naught. Okay, so ataupun you boleh tulis ln NA over NA naught. Okay, so just put it here, you will have this equation. Okay, for design of the equation in terms of the concentration of C. Okay, sekarang ni you nak dapat final equation for C only. You don't want any X or N here. Okay, so I will show you how you get it. Okay, so far semua okay ke? Are you following me?
Okay doktor, cuma slowkan sikit doktor.
Oh, saya berlaju sangat yang cakap.
Ya, saya macam laju sikit.
Okay, saya slowkan sikit. Okay, so daripada mole balance, remember yang kita dah simplify, so it become R. Okay, saya tulis sini lah, mole balance. Okay, so yang tinggal untuk ni batch tau, batch reactor, which is RAV is equals to DNA over DT. Okay, this is accumulation, this is the G itulah, which is the reaction. Okay, so from here we put it as one side for DT, naikkan dia. So DT is equals to DNA over with the RAV. Okay, so this is the first order. So you just replace dulu RA here, okay, with this one. Okay, so it becomes DNA over with the negative KCA times with this one V. Okay, so as I told you before, NA is equal to CAV. Okay, so sebab kita nak dapatkan dalam bentuk C sahaja, so we kena get rid of N. Okay, just replace this one lah dengan this. Okay, so it become DCAV over with the negative KCAV. Okay, so V ni kita boleh cancel. Okay, ini kena letak kat luar lah sebab volume dia tak berubah, so awak tak boleh nak differentiatekan V. So V ni kena letak dekat luar ni, so kita boleh cancel. So what remains is DCA minus KCA sama dengan DT. Okay, so daripada sinilah kita nak dapatkan in term of T sahaja, so kita kena integrate. So here we have a yang tinggal dt is equal to dCA minus KCA. Okay, integratekanlah dua both side. So it becomes F T naught dt is equals to, okay, keluarkan dulu supaya you tak confuse lah bila nak buat integration. Okay, yang mana ada satu value, constant value you keluarkan. So what remain is dCA over with the CA. Okay, so integratekan dia untuk CA at any t and CA0 at t0. Okay, kena samalah align atas ni. So it becomes integratekan 1 over CA dengan dCA. Okay, so daripada situ you akan dapat T is equal to minus 1 over K and then ln CA, okay, minus with the ln CA0. Okay, so boleh simplifykan jadi 1 minus 1 over K times with the ln CA over CA0. Okay, boleh ke? Up to here?
Boleh, Doktor.
Boleh, Doktor.
Okay, so sekarang ni instead of nak dapatkan in term of C, kita move to macam mana nak dapatkan conversion to X. Okay, I tak tahu kenapa equation ni dia merge dalam satu ni. Okay, alright, so kita start with more balance. Okay, seperti biasa. Okay, so RA, okay, V0 is equals to dNA over dt. Ini daripada more balance. Okay, so daripada sini kita nak tengok, kita boleh ubah dekat area sini. Okay, sebab kita nak X, in term of X. So what is NA? Okay, kita keluarkan dia. We have a dNA over dt. Okay, so D, keluarkan dia, dt, which is this one is NA0 minus with NA0 X. Okay, ingatkan NA is equal to NA0 1 minus X. Okay, so daripada situ, ni lah kosong. So it becomes negative dNA not X over dt. So kita tak boleh differentiate of NA0. So NA0 kena letak kat luar. NA0 dx over dt. Kita boleh tengok different conversion at different times. Okay, kita tak boleh tengok different NA0 at different time. Okay, so kena keluarkan dia. Okay, so this one is RA V0 lah. Replace dia lah dengan dNA over dt. Okay, so the red law is, ikut je step dia, red law is negative RA is equal to KCA. Okay, so the third one, remember apa dia adalah stoichiometry. Okay, so the stoichiometry would be CA is equal to CA0 1 minus X. Sekejap, nak minum air. Okay, so from here, kita tengok balik yang ni. Okay, kita put on the left side dx over dt, okay, is equals to negative V0 over NA0. Okay, ni I dah rearrange dia lah. Okay, times with the RA. Times with the RA. Okay, just rearrange daripada sini. Okay, then we have a dx over dt is equals to, okay, so this one, remember, kita boleh tukarkan jadi CA0 kan? So which equals to 1 over CA0 times with RA. What is RA? Negative KCA lah. Sebab sini positif, so kita terbalikkan dia jadi negative KCA. Okay, so kita boleh cancel this one. Okay, so what is CA? Tengok pada stoichiometry balik, 1 over CA0. Okay, times with the K. Okay, times with the CA0 1 minus X. Okay, so it become K times 1 over X and then this one. Okay, make sure you try to simplify first. Don't directly integrate it. Okay, sebab kalau you integrate terus nanti lagi macam bercelaru lah. So you kalau boleh try to simplify as you can, as much as possible. Okay, then baru you integrate. Okay, so from here you integrate in term of dx over with the K 1 minus X and also dt. Okay, so integrate, this one keluarkan. So that's why you will get at the end should be T is equals to 1 over K ln 1 1 minus X. Okay. So sebab apa you kena tahu macam nak guna C and X, dia ikut pada soalan. Kadang-kadang soalan tu tak beri you what is C and not, what is CA. So you can use this directly to get the T. So you don't, because this equation there's no C and not and CA terms. Okay. Sama jugalah macam yang previously, kalau tak diberikan X, you still can put the value of CA dengan CA not. Okay, kalau dia bagi nilai CA dengan CA not directly lah. Directly, okay. Okay. So this ideal batch vector, we can transform into a curve in order to know what is the area. Okay. So macam mana? Okay, remember basic equation of mathematics. Area is defined with the width times with the height. Okay, same like this one, we have width, dia punya adalah X. Okay, XA minus width 0. Okay, then we have a, katakan height dia adalah times with the 1 negative RAV. Okay, so daripada sini, the one that yang you dapat lah derivation dia. Okay, daripada negative RAV is equal to NA not dx over dt, asal dia yang ni. Okay, so you jadikan dia ni dah after integration, you akan dapat ni. Okay, so daripada sini macam ni kita boleh dapat area is equal to T over NA not. Okay, adalah kamu just rearrange sahaja. So T over NA not, okay, bawakan dia ke bawah, is Fxa not, okay, apa tulis ni, XA not, okay, dx, okay, V dengan RA ni kita boleh bawakan keluar lah sebab kita nak differentiate between X je. So times with the 1 negative RA times V. Okay, so ini kita integrate of dxa, dia akan jadi X kan, XA, so adalah XA to 0, so that's why dia akan jadi XA minus with the 0, okay, times with the negative RAV. Okay, so ini adalah width dia and this one is dia punya height. So dapatlah area dia. Okay, faham ke? Okay, so just tengok aja mana X dia, mana Y dia. Okay, so for this one, yang bawah ni pula constant density system only. Ini in term of kalau C dengan sebelum tu I explain you XA, sekarang ni in term of CA0 dengan CA. Okay, so area dia akan berubah jadi T sahaja. So this area is equals to T. Okay, tengok balik sebelum ni. Okay, for this one we have this. Okay, yang kita simplify lah. We have a DT is equal to DCA negative RA. Okay, so daripada situ ataupun you boleh tengok yang dekat sini. Okay, you akan dapat ni lah. Okay, so kita ada T is equal to CA0 Fxa0 dx over negative RA. So sebenarnya kita boleh tukar X ni in term of C. Ingatkan tadi kita ada in term of conversion and in term of concentration. So kalau in term of concentration, you will have negative CA0 okay, dCA over negative RA. Okay, so awal-awal ni yang daripada equation ni you dah kena tukar dah in term of C. Okay, sebelum you jadi integration ni. Okay, nanti you try lah yang buat tu. Okay, ada tunjuk tu. Okay, so daripada sini Allah tak nampak pula, saya pergi ke sini lah. Okay, so daripada sini we have a T dengan CA0 kan. Okay, so T is equal to CA0. Okay, so you integratekan dia dulu dengan FCA. Sekejap ni CA0, I buat ni dulu lah, integrate dulu lah satu-satu. CA0, okay, jangan lupa yang ada negatif, ikut yang mana? Ikut yang ni okay, DCA, okay, you pecahkan negatif RA boleh letak kat luar. Okay, so you integrate yang ni. Okay, so sini ada negatif kan. Okay, so kalau you integrate biasa, sepatutnya dapat CA minus CA0. Tapi disebabkan dia ada negatif kat luar ni, so you adjustkan dia jadi terbalik. C, jadikan instead of macam ni, you jadikan dia CA0 minus CA. Okay, sebab dia ada negatif kat luar, ni ada negatif. Okay, so daripada situ kita akan dapat CA0 minus with the CA. So ini akan mewakili dia punya width. Okay. And then times with the 1 over negative RA yang kita keluarkan tadi, this would be the height. So this area is the T yang remaining here. Okay, so faham ke? Are you clear before I proceed to the next slide?
Bolehlah sikit-sikit ada.
Aha, yang mana? You ada kekeliruan yang kat mana, area mana?
Tak ada kekeliruan ada, cuma tak dapat nak catch up sikit-sikit.
Oh, okay. Tapi so far you dapat the whole idea ke?
Bolehlah. Dapat.
Okay, saya faham sebab memang mula-mula memang agak keliru tu adalah sebab dia banyak equation involved. Tapi tak apa, saya terangkan ni, nanti you try to try buat lagi sekali, tulis lagi sekali sendiri, nanti you akan lebih faham. Okay, tak apa, saya faham yang mula-mula memang macam ni. Okay, that's why I will give a details explanation one by one ni lah. Alright, okay. Okay, tapi basically apa-apa pun you kena tahu more balance lah. Okay, daripada situ you akan buat simplifykan dia, you akan expandkan dia and simplifykan dia and integratekan dia. Okay, so sebelum integrate, of course you kena jadikan dia differential equation. Dia kena ada dx over dt, dv, macam tu lah lebih kurang. Okay, tapi untuk batch reactor, you kena concentrate untuk dx dengan dt. Okay, ataupun DC. Okay, alright, tak apa, kita one by one ya, kita go. Alright, no worries, nanti you boleh tengok balik recording ni. Okay, so this algorithm to estimate reaction time. Okay, so this is comes from the mole balance. Okay, yang kita dah ni lah rearrangekan dia in term of dx over dt. Okay, kita tak boleh dv sebab batch reactor tak ada dv, so kita concentrate dx over dt saja. Okay, ataupun DC ke over dt pun boleh. Okay, jangan lupa kita ada X dengan C lah term. Okay, so first order here, red law. Okay, so you will combine this one to get this. Okay, sebab apa kita nak dapat this differential equation? Daripada differential equation lah kita boleh integrate in term of X and also in term of dt. Okay, that's why at the end you akan dapat ni lah, ni ayat dah tunjuk lah. Okay, this just nak recap je. Okay, so yang sebenarnya yang menentukan perbezaan dia adalah kalau you tengok dekat more balanced rate law stoichiometry between first order dengan second order adalah dekat rate law sahaja. Yang tu yang I cakap, you kena tahu more balance yang paling penting dan juga stoichiometry. Okay, sebab dia akan apply balik, masuk balik CA ni, yang ni pun dia akan masuk balik CA ni. Okay, so the step is the same. Okay, you have to combine all the more balanced rate law stoichiometry. It's just that when you do the integration, it will be different lah. Because this one contoh case times 1 minus x, tapi this one is C and not 1 minus x kuasa 2. Okay, so this one I akan show in the next slide macam mana boleh dapat ni. Okay, so let's say we have a design equation in term of the C. Okay, this is applicable untuk pula second order reaction which is KCA2. Okay, so again we start with mole balance. Okay, mole balance. Alright, so the mole balance kena ingat sampai tua, RAV is equal to, saya pun dah tua ni, DNA over DT. Okay, so daripada sini kita nak rearrangekan dia in term of C. Okay, you kena tukarlah NA ni. Okay, so kita kena settlekan ni dulu. Yang ni tunggu dulu. Okay, so settlekan dia, put it this one dekat V. Sebab RA ni dah tak ada masalah sebab dia dah ada KCA kuasa 2. Okay, so it will become RA is equals to 1 over D DNA over DT. Okay, so daripada sini you have D. Okay, sebab V is equal to V naught. Okay, so D kita boleh naikkan lah NA over V naught over DT. Okay, so daripada sini kita boleh dapat this one is equals to DCA. Okay, over with DT. So this DCA over DT adalah represent to the RA. Okay, so daripada sini of course kita kena expandkan dia sebab RA ni kita tak settle lagi. Okay, so we have DCA over DT is equal to RA. So what is RA? RA is equal to negative KCA kuasa 2. Okay, sebab ni positif, so you pindahkanlah dia jadi sini negatif. Okay, pindahkan dia. Okay, daripada situ remember you kena buat apa nama dia? Kena buat ni lah apa nama dia? Integration. Okay, so from here put it one side 1 over K. Okay, so we have a DCA. Okay, kita letakkan CA kat sini lah, kumpulkan CA square. Okay, so kita boleh integratekan ni, yang ni kita naikkan atas dt. Okay, so this is T to 0 and this is CA to CA naught. Alright, so you kena tahulah macam mana nak integrate 1 over CA 2. Okay, DCA. Okay, kena tengok balik lah. CA negatif 2 plus dengan 1 kan, so dia akan naikkan negatif 1 sini, so that's why dia akan jadi negatif 1 over C. Okay, for CA. Okay, so you akan buat ni untuk itu of CA dengan CA naught. Okay, so daripada situ, okay, dah integratekan, you akan dapat negatif 1 over CA. Okay, for CA dengan CA naught is equals to negative KT. Okay, so daripada sini 1 over CA naught. Okay, remember sebab I tak nak jadi dia negatif, so I jadikan CA naught tu dulu. Alright, minus with the 1 over CA is equal to negative KT. Okay, so sebab kita nak T sahaja, so rearrangekan dia. T is equals to 1 over CA minus 1 over CA naught over dengan K. Okay, so this will be the answer. Okay, so basically you tukar je lah NA over DT ni jadi CA, DCA over DT. Okay, so sekarang pula in term of X. Okay, so sekarang ni saya akan tunjuk. Okay, ready semua? Okay semua?
Okay, doktor.
Okay.
Alright, okay. Tarik nafas dulu, okay. Okay, so kita start dengan mole balance again. Start je, mesti apa-apa pun dengan mole balance. Okay, so mole balance, remember dNA over dt accumulation is equals to the generation. Okay, so again lah, kita jadikan dia 1 over dV dNA over dt is equals to RA. Okay, this one kita jadikan dia single lah. Okay, so sekarang ni kita kena settlekan benda ni. Okay, saya settlekan dulu DNA ni ya. So DNA ni adalah D, you kembangkan, dia akan jadi darab dengan NA kan. So NA ni adalah kita expandkan dia NA naught minus with the NA naught X over with the DT. So this one kosong. So that's why DNA over DT is equal to NA naught dx over dt. Okay, so what is DNA dt adalah benda ni RAV. Okay, so daripada situ, okay, DNA dt ni adalah negatif RAV naught. Tak ada negatif. Kalau you tak sini negatif, you jadi positif. Kalau you tak sini negatif, you jadi positif. Okay, bagi saya lebih baik sini positif lah sebab RA terus masukkan ni je. Is equal to negative KCA, ikut pada you lah. Tapi nanti you arrange, you akan dapat benda yang sama juga sebenarnya. Okay, so daripada situ kita nak tukar jadi X. Okay, so dx over dt. Okay, kita bawa ni dalam satu side, left side. We will have negative VO. Alright, ni V besar atau volume over with the NA naught times with the RA. Okay, so RA ni sebenarnya KCA kuasa 2, negative KCA kuasa 2. And this one kita boleh change into CA naught. Okay, remember CA naught is equals to NA naught over with the V naught. Okay, so jadikan dia akan become dx over dt is equals to minus 1 over CA naught. What is RA? RA is negative KCA squared. Okay, so this one, okay, kita dah ada red law. Ni nombor 2 is red law. Okay, nombor 3 adalah stoichiometry. Okay, so tukar CA ni. So you will have, okay, this one kita boleh cancel awal-awal lah. Positif dia jadi positif lah. So jadi K over CA naught. Okay, what is CA kuasa 2? Which is a CA naught times 1 minus X kuasa 2. Okay, remember CA is equal to CN naught 1 minus X. Okay, so ada kuasa 2, kuasa 2. So this one, so tinggal K CA naught 1 minus X kuasa 2. So we have a dx over dt. Okay, sekarang kita nak cari in term of t. So dt tu naik ke sini lah. So dt here, alright. So this one is dx. Okay, so boleh masukkan 1 over k times CA naught. Okay, this one. Okay, so bawakan bawah lah. 1 minus x kuasa 2. This one f t naught. This one to x to 0. So you kena differentiatekan, kena integratekan 1 minus x squared dx. So dapat apa ni? Okay, so bila you integratekan ni, you akan dapat x 1 minus x. Okay, kena ingat balik lah matematik semua. Okay, so daripada situ, at the end kita akan dapat t is equal to, okay, yang kita integrate ni, x 1 minus x, okay, ni ada, so k times CA naught. Okay, so this is the answer. Okay, okay, faham tak steps dia?
Faham doktor.
Okay, faham. So kita go to exercise sikit. Okay, simple exercise sahaja. Okay, consider this elementary reaction A to B. Okay, so A to B means that kita boleh tahulah the red law would be negative RA is equal to KCA. Okay, to the power of 1. Sebab the first reaction, ni lah dia ada satu je. So the reaction process was carried out in a constant volume. Kita dah kata constant volume. Reactor of V. So V is equal to 200 meter cube. Okay, given the K. Okay, write down the rate equation for above reaction. So masukkan sahajalah rate equation is negative RA is equal to KCA. So is equal to 0.12 CA in 1. Okay, and B is calculate the time necessary to reduce the number of moles of A in a batch reactor to 99% conversion. Okay, so here the question does not provide you with CA naught. Okay, tapi dia provide you with X. So refer balik, this is the first order reaction, you pergi belakang lah, so which is this one. Okay, this one. Okay, in term of X. Use that equation. Okay, and masukkan balik the value for the X which is 0.99 and K. K is the 0.12. Okay, kita go lagi satu exercise sebelum kita break sekejap untuk steady state CSTR. Okay. Okay, so for exercise number 2, okay, given that 400 decimeter cube, okay, so this is the volume in a constant volume batch reactor. Saya dah mention this is a constant volume batch reactor. It's pressurized to 15 atm. Okay, this is the P with a mixture of 60% of A and 40% inert. Okay, means that this is in a gas system. Okay, dia dah mention constant volume, so dia bukan variable volume, dia bukan yang ada epsilon tu, bukan. Okay, that bukan. Okay, so this one is a mixture which is YA0 of 0.6%. Okay, so the gas phase reaction is carried out isothermally. Alright, 3 to 7. Okay, there is no changes in in thermal. Okay, by assuming that an ideal law is valid, calculate number of moles of A in the reactor initially. Okay, so you kena dapat what is NA0. Okay, then calculate the initial concentration of A. So what is CA0? Oh, sorry. So what is CA0? Kita tak tahu. Okay, lepas tu kita kena cari calculate the time necessary to consume 80% of A. So dia dah bagi X, dia dah bagi K. Okay, so tengok pada R dia. R dia bagi decimeter cube, ATM mol dot K. So temperature kena convert to Kelvin. So 273 plus with the 327. Okay, so you will have berapa Kelvin ni lah. Okay. So saya dah bagi satu contoh untuk yang konsum volume biasa untuk ni X, yang ni saya bagi satu contoh lah untuk yang berkaitan dengan gas phase. Okay, so kita start dengan ideal gas law punya equation. Kenapa ni? Okay, alright. So untuk A kita kena cari what is NA0. Okay, so tengok balik pada ideal gas law punya equation, is PV is equal to nRT. Okay, so kalau kita start dengan total dia, total system. So it should be PV, alright, is equals to NTRT. Okay, tapi kalau ada gas, kita in term of fraction. So kita tak boleh guna total, kita kena convert jadi NA0 over NAT. Okay, so remember from topic number 3, I suruh you remember this equation. YA0 is equal to NA0 over with the NT. Okay, so replace NT ni dengan is equal to NA0 over YA0. Okay, so kita put aside NT is equals to PV over RT. So NT replaced with NA0 over YA0 is equals to PV over RT. Okay, so kita nak tahu what is NA0. So NA0 is equal to YA0 times with the PV over RT. Okay, so just masukkan this is 0.6, P tu berapa tak ingat lah. And then V pun dah diberi, R pun diberi, T pun dah diberi. So you kena dapat the answer should be 73.17 mole. Okay, so this is the value lah of A. Okay, so for the B, okay, kita boleh guna balik daripada sini. Okay, sebab CA0 is equals to NA0 over V. Okay, so daripada situ kita tahu what is NA0. Okay, so NA0 adalah this one. Okay, so NA0 is equal to YA0 times with the P times with the V over RT. Jangan lupa kita ada V tadi per dengan V. Okay, so from here we can cancel the V. Okay, yang remain is YA0 times with the P over R times the T. Okay, so just masukkan value. You should have the value for the CA0 is 0.183 mole over decimeter cube. Okay, and the last one is to get the T. So simple je, guna T is equal to 1 over K ln 1 minus X. Okay, so you kena dapat around 130.85 minit. Okay, so far faham?
Faham, Doktor?
Okay, so saya bagi you break sekejap 2 minutes. Boleh ke 2 minutes cukup tak? Bolehlah sesuap nasi ke, seteguk air ke, okay? Alright. Nanti saya sambung. Saya tak nak offkan record tu. Saya takut tiba-tiba nanti saya terlupa nak on balik. Okay, saya leave it as it be, okay? Alright, boleh rehat sekejap. Okay, is it okay to proceed?
Okey doktor, boleh.
Boleh? Okay, yakin boleh. Alright. Okay, so kita start dengan steady state CSCR pula. Okay. Okay, so kalau perasan dalam saya punya slide, saya memang akan bagi ruang slide kosong. So kosong tu you boleh tulis lah balik apa yang saya tunjuk tu, okay, supaya nak lebih faham lah. Okay, so this one is a continuous tank reactor, CSTR, okay, steady state. Okay, so the rules is operate at steady state, okay, condition do not change with time. Okay, you can see kalau throughout the time, the volume does not change. Okay, still remain the same. Okay, at the same time, there's a in and out. Okay, so the accumulation of course zero sebab dia masuk and keluar, so tak ada accumulate dalam sini. Okay, that's why it becomes zero. Okay, so the reaction is perfectly mixed. There's no spatial variation in the rate of reaction. Okay, so dia sama juga macam konsep dekat batch reactor. Okay, so V dia adalah sama throughout the reaction. Okay, so this one would be RAV. Okay, so daripada sini you can cancel lah. This one is 0. Okay, and this one is the RAV. Okay, this one remains. Alright, so this would be called as algebraic function. Okay, so the special CSCR ni dia tak ada in term of D and juga integration. Okay, so how do we get this one? Okay, so V is equal to Fa0 minus Ra. So what is Fa? Fa is equals to Fa0 minus with the Fa0x. Okay, so you have this one lah. Okay, replace for Fa. Okay, so this one ni apa pula saya pada sini. Okay, so tinggal ni kan ni negatif kita positif, so dia akan jadi Fa0x over negative Ra. Okay, so this is the V lah. Alright. Okay. Then we move to the next slide. Design equation in term concentration C and volumetric flow rate. Okay. So kena remember what is C. C is equal to molar per second. Okay. Over with the volumetric flow rate. Okay, so this is mole per time. This one is decimeter cube over time. Okay, so this just you masukkan balik sebab V is equal to Fa0 minus with the Fa over with the negative Ra. So just replace this one with V0 Ca0. Okay, this one V Ca. Okay, so that's why you get this equation. Okay, so for liquid phase with constant volume, okay, this one is equal V0. Okay, so V besar ni, okay, so this one you can expand it first. Okay, daripada equation yang ni, Ca is equal to Ca0 minus Ca0x. Okay, so daripada situ kita boleh cancel this one jadi positif. So Ca0 V0 X over negative Ra. Okay, jangan lupa dia ni darab kat V0 ni kat luar, so dia kena V0 darab Ca0 X. Okay, over Ra. Okay. Okay, so design equation in term of tau. Okay, so this one in term of tau. So tau macam mana kita boleh dapat? Actually is tau is equal to volume over with the volumetric flow rate. Sebab apa? Volume is decimeter cube. Volumetric flow rate is decimeter cube over with the time. That's why you will have time dekat sini. Okay. So you akan dapatilah here. Okay. So negative Ra is equal to Ca0 V0 X over Kca. Okay. So Ca ni you boleh tukarlah. Okay. Ni daripada you gantikan negative Ra daripada sebelum ni. equation ni equation 4.9. Okay, so you will have this one. Okay, so CN0 ni you can cancel it. Okay, so yang remain is V is equal to V naught X over V the K1 minus X. Okay, sebab kita nak dapatkan ni, kita just bahagikan dengan ni. Alright, so dia akan dapat T. So T is equals to, okay, tinggal ni kita dapat ke bawah kan. So tinggal X over K times 1 minus X. Okay, so ni lah macam mana kita dapat equation 4.10. Okay, tapi this one applicable for first order only. Okay, dah second order dah cerita lain dah. Okay, so you kena replace sajalah bawah ni. Kalau second order dia akan jadi Cn0 y minus x squared. Nah, macam itulah. Okay, so design of equation. Okay, so this is design equation. Okay, remember design equation kena start from the mole balance. Okay, so you rearrangekan to get the V. Okay, so in terms of the conversion, you should have this equation. Okay, so reactive sizing the volume of CSCR can be calculated from Fn0x versus X. Okay, so kita ada volume dia V is equals to, you pecahkan dia Fa0 over negative Ra times with the X. Okay, so this X would be the x-axis and Fa0 over negative Re would be the x-axis. Okay, so kalau you ada curve macam ni, you dah plot kan. So kita ada different x. Contohnya kita ada okay, kita ada different x, kita ada different Fa0 over negative Re. Kita plot lah sini maybe 0.0, 0.1, 0.3. So kita ada plot sini. Sebenarnya the volume yang kita counter adalah here, the whole one. Okay, itu adalah volume. Tapi kalau macam PFR, volume ni kita consider bawah dia saja, sama dengan batch. CSCR dia lebih volume. Sebab dia counter semua ni. Okay, sebab dia directly darab lah terus. Okay, dia tak ada differential, dia tak boleh, dia tak kira macam kecil-kecil, tak ada kira semua sekali sebab dia bukan under differential equation ataupun kita boleh integrate dia. Okay, so automatically area dia adalah V lah. Area dia V. Macam tadi kita buat satu-satu kan, ingat tak? Untuk batch. Okay. So, Levens spills plot. Okay, sebenarnya part of Fogler punya book, you also can refer to Levens spill. Okay, tapi cuma Levens spill ni dia very complicated sikit lah, dia very detail. Okay, so Levens spill plot graphical method to determine the volume of reactor. Sizing a chemical reactor is to determine a reactor volume to achieve the given conversions or determine a conversion for a given reactor volume. Okay, so sizing ni you boleh sama ada to determine volume punya reactor ataupun kita boleh determine what is the conversion, the X. So the volume of CSTR and the volume of a PFR can be represented as the shaded areas in the Levens spills plot. Okay, so okay, next slide lah akan cerita. Well, this is what we call as Levens spills plot. Okay, so we have a Fa0 minus Ra. So ini I terangkan lah, ada x-axis dengan y-axis. Okay, so the area would be the whole this one, which is the height times with the width. Alright, and whereby x ni kita boleh juga jadikan dia what is x, sebab x is equal to macam Cn is equal to Cn0 1 minus x. So rearrangekan dia, you akan dapat x equal to Ca0 minus with the Ca over Ca0. Okay, so this Xa adalah inilah. Okay, sebenarnya itulah yang dia nak cerita. Okay, so daripada sini sebenarnya you boleh translate into next graph macam mana adalah dengan katakan this we have Vf0. Okay, saya terangkan dulu lah. V is equal to Fa0 times the X negative Ra. Okay, so daripada sini kita kembangkan what is Fa0 sebab kita nak in term of C sekarang ni. C dengan X sahaja. So kita kena tukarkan dia jadi Ca0 lah. Okay, so Ca0 times with the V0. Okay, remember kita ada CA0 B0, F equal to CA0 B0 times with the X. X yang sebelum tu lah previous slide I tunjuk, which is CA0 minus with the CA over the CA0. Okay, over with the negative RA. Okay, so sekarang ni macam mana kita boleh dapat area dia tau. Here, kalau you nampak this one tau. Okay, so this one the V0 kan. So V over V0 is equals to, okay, so this one kita dah bawa ke bawah perkara V0. Okay, this one kita boleh matikan. Okay, so that's why tinggal CA0 minus CA, okay, over with the negative RA. Okay, so you will have this one as the X and this one is the Y and this one will be the area. Okay, faham ke tak?
Okey doktor.
Okay, so itulah macam mana nak dapat. Sebenarnya kan dia sama je, you kena play around with the equation. Okay, kalau in term of X, X, kalau in term of the C, C. Okay, so benda tu sebenarnya ada significant, you boleh jadikan dia sebagai area. Okay, sebab kita ada untuk width and height dia. Okay, okay, so for example, okay, kita ada sizing CSCR. Okay, ni boleh refer dekat formula juga. Okay, so the reaction A to B is carried out in a CSCR. Given that molar flow rate of A is 0.4 mol per second. Okay, means that this is the FA0. Okay, so FA0 is given. Using the data in the following table. Mana table dia? Allah, tak keluar pula. Sebenarnya dekat table ni, tak tahu dah kenapa hilang kat sini. Saya pun perasan. Okay, so okay, table dia adalah begini. You should have X negative RA, okay, dalam mole over meter cube dot second. Okay, we have a 0, 0.1, we have a 0.2, 0.4, 0.6, 0.7, and then another one we have a 0.8. This one is 0.45, sorry, okay, then 0.37, 0.3, 0.195, 0.113, 0.0079, 0.05. Okay, so daripada sini, remember volume adalah FA0 over negative RA times X. Okay, so kita nak kena ada plotkan ada X axis dengan Y axis. So this one would be the Y and this one would be the X axis. Okay, so make sure you buat lagi satu kolom kat bawah ni for negative FA0 over RE. Okay, so you kena ada 0.4 over 0.45 means 0.67 and so on. Okay, so daripada situ you kena plot lah and then you akan dapat this graph. Sekarang ni dia kata dia nak achieve 80%. Okay, means dia dekat maximum 1. So you akan plot, dapatlah titik dekat sini. Okay, so actually the volume is cover like under this rectangle. Okay, so sebab apa, macam mana you nak kira? So V is equal to FA0 times X, X kan? Okay, so from here, what is FA0 per RE, which is Y is, FA0 adalah 0.4, okay, times with the, okay, times with the 1 negative RE, okay, so which is this one 0.05, so you bahagikan lah siap-siap, okay, you akan dapat 20, okay, times with the X, so you will have the volume here. Okay, faham?
Doktor, saya tak jelas mana doktor.
You apa? Tak dengar?
Saya tak jelas yang table tu doktor.
Oh, yang table. Okay.
Uh-huh.
Sebenarnya dalam table question ni dia given only for X dengan negative RA. Okay. Alright. So kalau kita tengok, okay, ni sebenarnya dalam soalan memang dah ada ni lah value ni. Okay, kalau you tengok volume is about, untuk CSCR is equals to FA0 times X over negative RA. Okay, so kalau kita nak construct a graph, kita tahu volume dia, kita kena tahu apa Y axis mana satu, X axis mana satu. Okay, so berdasarkan yang I terangkan level speed yang belakang ni. Okay, so this would be the y and this point would be the x. Okay, so sekarang y-axis you kena kira balik sebab y is equal to FA0 over negative RA. Sekarang ni dia bagi value untuk negative RA. Okay, so daripada situ you kena buat lagi satu kolom lah kat bawah tu, which is untuk kira FA0. Okay, ataupun sekali you nak times boleh, tapi kena dengan ni lah RA. So this one make sure you kira dalam bentuk 1 over RA, you perkan dia. So 1 per 0.45, 1 per 0.7, and then you multiply dengan FA0. Okay, so setiap ni akan ada satu value setiap berbeza untuk ni FA0 times 1 negative RA. Okay, faham ke up till this point?
Kiranya doktor FA note tu yang 0.4 tu kan doktor?
Ya, betul, dia fixed value.
Okay. Faham doktor?
Okay, so bawah ni faham ke tak yang macam dapat V ni?
Faham.
Okay, alright. So
Okay. Terima kasih doktor.
Okay, no problem, sama-sama. Okay, so that would be the volume lah. Okay, baru keluar ke? Okay, alright, table ni aduh, main cak-cak pula. Okay, so and then we have exercise 3. Okay, saya tengok macam exercise 3. Saya dah asingkan. Okay, so exercise 3, the following reaction takes place in a CSTR A to B. Okay, so pure A is fed to the reactor with molar flow rate is 10 mol per minute. Okay, so this is the FA0 lah. Okay, so this is the CA0. Calculate the conversion of reaction if the volume of the reactor is V. So dia dah give you the volume punya value, which is 500. Okay, maaf lah tersasul lah. Okay, so dari sini V is equal to FA0 X over negative RA. Okay, so this is red law dia, negative RA is equal to KCA. So replace sahaja. Okay, which is FA0 times with the X, okay, over with the KCA0 1 minus X. Okay, so masukkan sahajalah equation ni, you akan dapat what is the volume. Okay, the direct sahaja, senang sahaja. Okay, for exercise 4 pula, a gaseous speed of a pure air, given that this is a CA0, okay, enters a CSTR with this volume. Okay, write as a follow. So we have a A to B, which is negative RA, is equals to 0.05 Ca to the power of 2. Okay, so this one dia takkan akan jadi variable volume, okay, sebab kalau you kira pun del, dia akan jadi kosong. So kan epsilon is equal to YA0 times with the del. Okay, so del ni kalau you buat ni, dia akan jadi kosong. So this is automatically ni adalah constant lah, kita treat as a constant volume. Lagipun dia dah cakap pun, okay, constant volume. I nak cakap je lah, nak proven kalau you nak tahu juga macam ni dia constant volume, dia letak je del is equal to, this one is 1 and 1 kan. So 1 minus 1 akan jadi 0. So tak akan ada epsilon, dia akan 0. So dia tak akan ada V is equal to V0 1 plus epsilon. Okay, so akan 0. Dia akan sama lah. Okay, so constant volume. Okay, so from here, K is given. Okay, so just masukkan je lah. V is equal to FA0 times with the X over negative KCA. Okay, and then okay, CA is kuasa 2. So we have volume dah ada. So kita letak sini 2 lah. 2 here. So FA0 kita tak tahu. That's what we need to get. Times with the X. Okay, and then negative 0.005 CA0 1 minus X kuasa 2. Okay, so ni kuasa 2. Alright, so as we know, X kita boleh convert it, which is X is equals to CA0 minus with the CA over CA0. Okay, so daripada sini you boleh try to rearrange it, okay, to get rid of the X ni lah. Okay, so you boleh dapat lah what is the answer of the FA0 ni berapa. Okay, alright, sebab dia pun dah bagi CA here. Okay, tapi kalau you tak nak convert CA pun tak apa, rasa tak payah convert, sorry, you tak payah convert, ni direct je, apa I cakap ni. So should be V is equal to FA0 X over negative K CA2. So confirm banyak sama dengan now. So CA ni boleh guna je sebab dia dah ada CA here. Okay, so replace sahajalah. Okay, masukkan dapatlah nilai X dia berapa. Bad network ke? Ada lagging ke?
Okey je doktor.
Oh ya ke? Kenapa tak ada notification bad network quality? Okay, so kita go to the next one, exercise juga. Okay. Okay, so exercise number 5 ni, the elementary liquid phase reaction 2A is equal to B, okay, which means this is the second order reaction. Negative RA is equal to Ka Ca kuasa 2, okay. So it's carried out isothermally in a CSTR. Pure air A enters the reactor at 30 decimeter cube per second and 0.2 mole over decimeter cube. So this one would be the Ca0 and this one would be the ni apa ni? Ni volumetric flow rate. Okay, tengok pada unit you akan tahulah. Okay, so daripada first tu you kena calculate the CSTR volume. Okay, to achieve 88% conversion when K is equal to 10. Okay, so tengok balik which is W is equal FA0 X over negative RA. So FA0 X is equals to K times with the Ca0 1 minus X kuasa 2. Okay, so semua kena kuasa 2 lah. Okay, so you just masukkan the value lah of the FA0 X. Okay, K pun dah given, Ca0 pun dah given, so you boleh masuk dapat nilai volume. Okay, so for FA0, okay, so for the number 2, okay, you kena dapat what is T. Okay, ataupun kita panggil tau pun boleh lah, ikutlah. So remember tau is equals to V over V0. Okay, so this FA0 you kena tukarkanlah kepada Ca0 times V0. Okay, so daripada sini you just guna sebab apa nanti V ni kita akan per dengan V0 lah, dapatkan tau. Okay, so what remains, okay, okay lah, I buat back semula lah. V is equal to Ca0 V0 is equal K Ca0 kuasa 2 1 minus X kuasa 2. Okay, so this one akan tinggal bawah lah, satu, and this one kita bawa ke bawah. So T is equals to V over V0. Alright, okay, is equals to 1 over K Ca0 1 minus X squared. Okay, so masukkan je lah value, dapatlah nilai T. Okay, faham ke?
Doktor, kenapa dia second order?
Sebab ada 2A. Ada 2 ni.
Alright, thank you.
Okay, tengok pada stoichiometry ni. So, kalau saya 3A equals to B, so dia akan jadi inilah, akan jadi letak sini 3. Okay, tengok pada stoichiometry ni. Alright. Okay, so exercise 6 ni try buat sendiri. Okay, itu answer dia, 487. Okay, try. You remember start dengan, sama je method dia, start dengan mole balance. Okay, lepas tu tengok pada red law dia. Okay, sekarang ni dia ada B. So, apa stoichiometry untuk CA and juga CB. Okay, Allah bagi teruk tulisan saya. Okay, so you can try tengok ni, masukkan balik dekat combine semua ni in order to you to get the V. Okay, try buatlah untuk dapatkan 487 ni. Okay. Okay. Alright. So far okay ke untuk CSTR? CSTR ni macam direct sikit lah. Dia tak ada, sebab dia tak perlu integration, differential equation. Okay, semua okay ke?
Okay, doktor.
Okay, so saya akan stop pukul 12 lah. So kalau mana yang saya tak habis tu saya akan record dan saya akan bagi ke awak juga. Okay, sebabnya kita Khamis kan cuti di Pawali. Okay, so semua orang mesti nak enjoy kan makan muruku semua tu. Okay, so tak apa. So that's why saya akan bagi the remaining yang saya tak sempat cover ni, saya bagi dekat, saya bagi recording nanti. Okay. Saya okey. Lepas tu saya akan bagi tutorial lah. Ingat kita akan ada tutorial next week hari Selasa untuk tutorial 3 and 4. Alright, saya cuba bagi tutorial punya question sama ada hari ni atau esok lah. Okay. Then we have a plug flow reactor. Plug flow reactor ni dia berbeza sikit dengan CSCR dengan batch reactor. Okay, so ni ada gambar dia. Okay, sebenarnya dia akan flow macam ni. Okay, dia pun akan ada flow ke atas ni. Lepas tu on the same time sebenarnya dia ada radial juga. Okay, dia berpusing juga dalam sini. Okay, so dia ada sini ada FA0 and then keluar sini FA. Okay, tapi we don't have accumulation dekat sini. Sebab dia continuous kan. So this one should be 0. Okay, so kalau you tengok ni dia adalah unsteady mode. Okay, whereby at T1 dia akan jadi C1, C2, C3, C4, C5. So kat sini dia akan ada different time of fraction and different volume. Okay, that's why we call as unsteady. Dia tak stable lah. So the concentration varies continually in the axial direction through the reactor. No radial and spectral variation in reaction rate. Okay, so kalau ni, sekejap saya movekan ni. Nampak pula. Okay, so this is FA0. Okay, masuk, so dia akan ada change in the volume. Okay, that's why kita boleh integrate dia. Sebab setiap value of A kat setiap time ni, dia akan berbeza volume. So, this one kita boleh juga bagi tahu is equal to RA change of A. Okay. So, ni lah equation dia. Okay, so axial ni maksud dia ni longitudinal. Okay, remember kita just assume this is either reactor, kita tak consider pun ada radial. Tapi in the real situation sebenarnya dia ada radial. Okay, kita berpusing-pusing. Okay, so where the differential volume delta V is shown below. Okay, so daripada sini kita tahulah which is FA0 minus with the FA plus with the RA is equal to 0. Okay, tak ada accumulation. Okay, so this is we call as differential volume. Okay, ataupun plug lah kita panggil. Alright, so daripada sini, okay, ini adalah dia punya in lah. Okay, and this one is the out one. Out dia akan tambah dengan apa yang change between this differential volume. Okay, so this will be the out. Okay, so this one is the RA and this one should be 0. Okay, so yang remain adalah FA0 minus F, okay, is plus with the RA is equal to 0. Okay, tapi ini kita boleh remain juga ataupun FRA dV is equal to 0, FA0 minus with the FA. Okay, so in order for you to differentiatekan ni, of course you can integratekan ni, you kena ada differential equation. Okay, so ini you kena transform into juga dV. Okay, so for example kita ada kita nak buat dia d over dV is equals to FA0, okay, minus with the FA, okay, is equals to yang ni kita dah bawa dia ke sana, which is the RA. Okay, so daripada sini dV tu kita dah bawa ke bawah lah. Dia pindah dulu ke sini, lepas tu kita bawa dia ke bawah. So at the end, ini kita akan zerokan, ini kita boleh keluarkan dia, which is dia become FA0 minus with the FA0 X. Okay, remember kita tak boleh FA0 over dV kan, so tak ada, yang tinggal ini sahaja. So that's why dia akan become negative dFA0 X over dV, tapi kita keluarkan F0 ni ada single value kan, so kita jadikan dia FA0 negative dx over dV is equal to RA. Inilah macam mana you dapat equation tu nanti. Okay, ke saya ter-advance sangat. Sebenarnya tu slide depan ni tapi saya dah over sikit lah. Apa explain. Okay, so sebenarnya inilah alkisah dia. Okay, so this one represent the DFA over DV. Okay, sebab you tak boleh biarkan dia FA not minus FA je, macam you nak differentiatekan dia, macam you nak integratekan dia. So you kena jadikan dia differential equation. Okay, so daripada sini adalah bila delta V approach to 0. Okay, ni mathematically lah. Okay, in the function of fx. Sebab apa you kena tahu function of fx ni, nanti you akan guna Simpson rule. Semua itulah numerical method nak kira size nanti. Okay, so you can tahu lah define what df over dx. Okay, so at the end you akan dapat ni. Okay, ini adalah starting daripada yang I buat tadi lah, which is negative FA naught yang tinggal dx over dv is equals to RA. Okay, ni yang saya expandkan dia lah, which is d FA naught minus with the FA naught x over dv is equal to RA. Okay, ni ikut je lah yang macam yang saya buat ni. Saya expandkan dia jadi d ni. Okay, ni bawa ke sini dulu. Alright, RA kita tinggalkan seorang-seorang, dv tu kita bawa ke bawah. Okay, so kita tukarkan ni jadi differential equation with respect of the change of v. Okay, so itu yang you akan dapat lah equation. Selalunya kita akan refer this one as this one. Ingat yang ni lah. Okay, faham ke? Yang ni sebenarnya sama je macam ni, cuma dia tak expand lagi macam ni. Okay, faham?
Faham, Doktor.
Okay, alright. Okay, so this is the differential equation. Ni yang I terangkan lah tadi. Macam mana you integrate lah. Okay, ni cara dia lah. Okay, yang buatkan ni jadi d over dv. Okay, alright. Sebab basically daripada equation asal lah, we have FA naught minus with the FA plus with the RA dv is equal to 0. Okay, sebenarnya ni lah dapat dia. Macam mana dapat tu daripada sini lah. Okay, so kita buat sesuatu macam tadi juga. Kita try to what do you call it, design equation in terms of conversion x if it's given that the rate law is a first order. Okay, so this is for liquid phase, constant volume. Okay, volumetric flow rate dia akan sama. Okay, same as the initial one. Okay, so the first one, remember, starting from the mole balance. Okay, so dFA over dV, ataupun you nak terus direct tadi pun boleh juga, sebab you dah tahu kan apa dia benda ni. Sebenarnya keluarkanlah balik, D is equal to FA naught minus with the FA naught x, okay, over the dV is equal to RA. Okay, so this one tinggal, that's one tinggal, FA naught dx over dV is equal to RA. Okay, so second one, kita tahu kan it is rate law, so rate law dia is negative RA is equal to KCA. Okay, so for stoichiometry, CA is equal to CA naught 1 minus X. So combine semua ni, okay, masukkan balik dekat red mole balance, dx over dv is equal to negative RA. Okay, so what is RA? Masukkan balik, FA naught dx over dv is equal to KCA. Okay, so daripada sini kita nak jadikan dia simplifykan version dia. You boleh terus buat in term of liquid phase ni dalam bentuk, kalau dia bagi dalam bentuk ni means dia flow kan. Okay, so kalau boleh try to change this CA ni, jadikan dia dalam bentuk flow lah. Okay, so kita keluarkan dia akan jadi K. Okay, okay, remember CA is equal to FA over this one. Alright, so basically kalau FA naught dia akan jadi V naught. Okay, so daripada situ kita dapat FA naught Okay, 1 minus X over with V naught. Okay, so daripada sini sebenarnya ini adalah CA0 lah. Kalau daripada F, okay, concentration datang daripada FA0 kan. So daripada sini kita jadikan dia K CA0 1 minus X. Okay, so FA0 dx over dv. Okay, so this one kita boleh matikan dia melalui yang ni. Okay, so daripada sini we have a kita boleh jadikan dia this one bila jadi K CA0 over FA0 times with the 1 minus X equal to dx over dv. Okay, so faham ke?
Boleh Doktor.
Okay, boleh. Okay, so benda ni kita tukar kepada volumetric flow rate lah. Okay, so you buat integrate in term of X dengan V. Okay, so you will have, I rearrangekan terus lah, V F0, K CA0, okay, and then 1 minus X dx is equal to F dv. Okay, so that's why you akan dapat this equation. Okay, so at the end you akan dapat V is equal to, wait, K ln 1 minus X. Okay, so inilah. Okay, so ini CA ni you boleh pecahkan lah sebenarnya. This one is daripada FA0 over V0 1 minus X. Okay, untuk stoichiometry ni. Okay, so itu okay. Kalau untuk volumetric variable volumetric flow rate, dia akan a bit susah sikit. Okay, sebab sekarang ni dia ada variable volume. Okay, V ni dah tak bersamaan dengan V naught. Okay, so you kena refer back what is this one. So V is equal to V naught 1 plus epsilon X, okay, times with the P naught over P times with the T over T naught. Okay, so this is for variable volumetric flow rate. Okay, so sekarang ni kita nak derivekan dia, alright, nak dapatkan what is the volume, okay, of the gas phase ni dalam PFR. Okay, so first kali kita boleh assume lah this is isothermally dan isobaric. Okay, so kita tu, alright. So start with the mole balance again. So should be dFA over dV is equal to RA. Okay, so daripada sini kena ingat balik lah equation kita boleh simplify to dFA over dV is equals to negative FA0 dx over dV. Sebab mana dapat ni? Kita tengok balik yang ni. Ni. Okay. Okay, so RA ni adalah mewakili negatif FA0 dx over dV. Okay, so daripada situ kita tengok balik what is RA. Okay, so kita ambil daripada RA is equals to negative KCA. Okay, so in here apa tu CA? CA is equal to FA over V. Okay, ingat this is in term of flow. Okay, is equal to apa tu FA? Remember stoichiometry FA0 1 minus X. Okay, V0 sekarang V is equal to V0 1 plus epsilon X. Okay, so ni this one is 1 plus epsilon X. Okay, ni ada V0, sorry. Okay, so daripada sinilah kita boleh matikan dia. Okay, kita boleh dapat this one, masukkan balik kat sini. So negative K is equal to this one is CA0 lah kan. So CA0 1 minus X over 1 plus epsilon X. Okay, so this is for RA. Okay, so apa tu RA? RA is equal to FA0 dx over ni. So masukkan balik negative FA0 dx over dV is equals to negative K ni equal to RA which is negative K CA0 1 minus X, 1 plus epsilon X. Okay, so ini agak payah sikit lah. Kadang-kadang dia dah ada dah provide in the appendix lah. Selalu kalau contoh macam F2F punya final exam, kami akan letaklah appendix untuk kalau integration yang susah. Okay, tapi you kena tunjuk jalan dia lah macam mana nak kira. Okay, so daripada situ negatif FA0. Okay, ni kan sekarang yang kat sini. Okay, saya bawa ke bawah negatif KCA0. KCA0, alright. Ni just rearrange sahaja, naikkan balik sebab kita turunkan balik, naikkan balik. Okay, sebab kita nak jadikan satu side dx, satu side dv. Okay, so daripada sini ni boleh jadi v0. Okay, yang ni kita dah cancel lah negatif dengan negatif. So should be v0 over k f x0. Okay, 1 plus epsilon x over 1 minus x dx f VO dV. Okay, so you kena tahu macam mana nak integrate kalau ada per macam ni. Okay, so at the end, nanti you cuba je lah. Jawapan dia lah V. Okay, ni adalah V. So V is equal to V0 over K. Okay, times with the, ni dah lepas integrate ya. 1 plus epsilon ln 1 over X minus V. Okay, inilah yang lepas you integrate. Inilah jawapannya. Okay. So, kita boleh dapat juga in term of T sebab T is equal to V over V0. Okay. So, this one kita dah bawa ke bawah. So, tinggallah seorang 1 over K times with this one lah. 1 plus epsilon. Alright. Ln 1 minus 1 over X minus epsilon X. Okay. So, inilah jawapannya. Okay. Sebenarnya nak derive in term of ini agak mencabar sikit lah kalau untuk untuk X. Kalau C, untuk C tak berapa susah macam yang ni. Okay. Okay, so far are you following me? Okay, they're lost in world of Tambun. Okay ke tak sekarang?
Okay doktor.
Okay. Yang penting tu nak ikut je step yang more balance, red loss, stoichiometric, lepas tu combinekan dia. Lepas tu buatlah integration dia. Nak cari V atau nak cari T. Okay. So sekarang ni kita tukar pula kenapa? Ni. Ni lah sebenarnya, nanti you try lah tulis kat sini. Okay. Sekarang ni adalah untuk in term of C pula concentration. Okay, so start again lah. C adalah, dia punya ni dFA over dV is equal to RA. Okay, so daripada sini rearrangekan sahaja. C dV is equals to dFA over RA. Okay, so apa itu FA? Kena ingat, FA adalah CA darab dengan V. Okay, so CA darab dengan ni. Okay, volumetric flow rate over with the RA. Okay, bukan V besar atau V volumetric. So then we have a DCA. Okay, V ni kita boleh bawa keluar lah sebab dia single value sahaja. Okay, so over dengan RA tadi kita ada KCA. Okay, sebab kita ada first order. So RA right low adalah negatif KCA. Okay, so negatif KCA. Okay, so this is DV. Okay, so daripada situ yang ni kan you boleh terus daripada, tak perlu nak derive daripada sini, you boleh terus direct ke sini sebab kita nak tukar FA ni terus, tak ada masalah. Yang ni kita kena tukar dulu sebab kita nak dalam X. So make sure awak punya design equation ada X. Yang macam tadi boleh terus sebab F ni kita boleh tukar terus concentration. Macam itulah maksud saya. Okay, so daripada situ you derive lah which is F dV, V dengan kosong. So we have V, okay, keluarkan juga ni negatif K. Alright, yang tinggal hanyalah F dCA over CA. Okay, so daripada situ kita differentiate, kita integrate lah CA dengan CA0. Okay. Alright. So daripada sini you masukkan apakah itu CA. Okay, tapi dalam case ni awak boleh terus differentiate sebab kita dah ada CA dengan CA. Tak perlu dah susah nak tukar CA0 ke dulu. Okay, tukar lepas tu boleh. Dia macam ni tau. Benda ni dia kena main dengan equation. Mana you rasa dah boleh integrate directly, terus integrate. Okay, so daripada sini, okay, integrate of 1 over CA, you akan dapat negatif, you akan dapat ln CA. Okay, ni kan CA0 kan? CA over CA0, so you akan dapat ln CA0. Okay, so daripada situ you akan dapat disebabkan sini negatif, awak tak nak jadi negatif, awak nak jadikan dia positif. So sini kena tukar lah, sini jadi ni atas. So that's why you will have WK ln K, jadikan dia CA0 over with the CA. Okay, so this is the answer. Okay, so nak jadikan T senang sahaja, bahagikanlah dia. So T is equal to V over V is equal to 1 over K ln CA0 over CA. Okay, ni kalau untuk dapatkan T, ni untuk dapat volume. Okay, so up to here okay ke, clear ke? Sekarang pukul berapa? Okay, saya akan stop sampai steady state PFR sahajalah. Ada few slide sahaja, 6 slide macam tu. Okay ke? And then I akan continue with self-recording je lah. Alright, okay. So kita tengok pada next one. Okay, okay ni I dah derive lah. Sekarang self homework. Okay, saya akan discuss yang number 1 je. Yang number 2, number 3 tu you try buat lah. Okay, so sekarang ni derive volume of a PFR as a function of conversion for variable volume, gas phase, semua tu lah. Sebenarnya yang ni rasa kita dah buat dah. Yang 1 plus EX minus EX ni. Sekejap, dah buat pun saya check balik. Okay. 1 plus EX. Oh, dah buat dah. Sorry, itu kat slide nombor 44. So tak perlulah. Yang ni just derive sendiri. Okay, saya terus ke ni lah. Equation. Okay, so design equation kena ingat dFA over dV is equal to RA. Okay, inilah design equation. Okay, kalau in term of conversion, kita ada this one. Okay, remember I cakap kita ada dFA over dV. Tadi kita buat in term of concentration. Dan kita ada pula ni in term of the conversion X. Okay, so from here, this is the Lewis-Pilz plot. Okay, kalau Lewis-Pilz plot, V akan bersamaan dengan FA0 over negative RE times with the Fx0 dx. Okay, so that's why you nampak this will represent with this one. And this one represent with X minus 0 lah. So this one. X dengan 0. So this one will be the X and this one will be the Y. Okay, so this is how you get the sizing lah, the volume. Okay, so the area would be this one. So yang tadi saya cakap kalau CSTR, dia akan mewakili semua ni. So dia adalah bigger volume. Tapi kalau PFR, dia adalah smaller volume. Okay, area dia dekat bawah the curve sahaja. Dia tak represent the rectangle sebab CSTR tu dia tak boleh differentiatekan dia. So that's why dia kena semualah. Okay, so this is the one that I told you lah. Okay. Then we have this one is in term of macam mana kita dapat area ni in term of V over Fa0 ataupun T is equal to Ca0. Okay, so starting daripada Fa0 dx, okay, sebab ada x kan, so kita ambil yang dx over dv lah, is equals to negative Ra. Okay, so daripada sini kita boleh integrate lah, sebenarnya adalah Fa0 x over negative Ra, okay, is equals to V. Okay, kita dah bawa ke sana kemari, dia jadi macam ni lah. So you will have, okay, pecahkan dia. Okay, so ini bawa ke bawah. So negative RA, okay, times with the X is equal to V over FA naught. Okay, so this one is about the Y and this one is about the X ni, and this one akan mewakili the area which is a A. Okay, A adalah this one lah. Okay, so kalau you nak dapat interval of T, you tukarkan ni dengan volumetric flow rate lah, you akan dapat this one. Okay, so for this one, okay, same juga, kita ada FA naught times with the X over with the V, RA is equal to RA. So this one is negative, negative 1 over RA. Okay, so what is X? X adalah CA naught minus with the CA over with the CA naught. Okay, and then this one is V over with the FA naught. Okay, so kita boleh jadikan dia negative over RA. Okay, this is for Y, and then CA naught minus with the CA, this is the X. Yang lagi per ni kita naikkan atas dia sahaja. So dia akan jadi CA naught V over FA naught. Okay, so this would be the area. Okay? Okay ke? So far so good? Oh, so far so bad.
So far so doktor.
Tak apa, lepas ni boleh jadi so far so good. Okay, lepas you second time you tengok. Okay, saya rasa itu sahaja. Okay, so nanti saya akan buat self recording sendiri. Cuma lepas ni you more kepada, I terangkan secara ni, you akan belajar macam mana nak kira dari segi numerical. Okay, dia akan same thing, dia akan apply the same equation for to get the volume. It's just that you akan kira macam ni kan, contohnya ada ni kan curve, so you akan kira kecil-kecil dia. This one, X1, X2, X3, you akan jadikan dia kecil-kecil. That's why we call it as numerical lah method. Okay, to get the volume. Okay, it's just that you need to know lah how to apply macam mana nak guna equation numerical ni. So nanti saya akan buat recording briefing lecture sendirilah dan bagi ke awak. Okay, so far okay. Okay, kalau saya stop sekarang. Okay, so saya stop sekarang dan nanti saya akan buat record sendirilah. Mana pula ni? Okay, sekejap. Kenapa tak keluar? How to maximize that one? How to maximize? Oh, okay. Alright, stop sharing and then I stop recording.